in a string, if both ends of the string are connected with the mass and the situation changes, like these two masses are hanging up and they are, let's say, at rest state, means hanged by this rigid point, and there is similar case, but between both masses there is a spring. Now if I cut this string, this top string, then this will start to fall, and in that case, just after cutting this string, the tension in this string will change instantly, but in this spring the tension does not instantly change. It depends on the extension of this spring. So that's the first thing. And another thing is pseudo force and tension force. So tension force is, let's say there is a string here with let's say this is a pulley here, and a string is connected to this pulley in this manner, and there is some tension T in this string. So this pulley might be pulled in both directions in this manner. So whenever you cut a string, let's say this is the string with some tension T. So if you cut this string, let's say this is a massless string, and you cut this string from this point, then this end will be pulled by T tension in this direction, and this part will be pulled in this direction with T tension. Means toward the open end the tension would act. So if I take this rope with the T tension, so there will be some T tension in the downward direction and some T tension in this direction, and this T tension on this rope, this actually acts on this pulley. So this T tension is acting in this direction and also in this direction on this pulley, and if this pulley is connected to some mass, that force will directly go to this body. And if we want to calculate the torque, we can calculate the torque by taking the force acting at this point, one force T in this direction and one force in this direction at this end. So that's how tension acts. And another thing is pseudo forces. For example, if you take any linearly accelerating frame, means a particle which is accelerating in any direction, then if you sit on that frame of the body which is accelerating with some a acceleration in a direction, then in its frame all the bodies will have some pseudo acceleration minus a of that frame, and that minus acceleration would cause some minus am force on any mass body, and this a acceleration should be observed from any inertial frame. Inertial frame means any frame which has zero acceleration. From that, let's call that frame as ground frame. So from the ground frame, when you see this point, this is accelerating with some acceleration. So when you sit on this frame, you will see that this object will have some minus acceleration, pseudo minus a acceleration. And if you have some another accelerating frame, let's say with some a1 acceleration, and from this frame you will see that this object has some different acceleration, let's say a star. So this let's say a dash. So this a dash, if you sit on this frame, this does not mean that there will be some minus pseudo a dash acceleration in this frame, because this a dash acceleration was observed from this non-inertial frame, and it would be taken for the pseudo acceleration. Only that acceleration would be taken which is observed from the non-accelerating frame. So from the non-accelerating frame, this is accelerating some acceleration. So if I take this frame, the pseudo acceleration would be minus a. So that's the first thing, translating acceleration. Let's say there is a particle here, this is rotating in a circle with some omega acceleration. So this body is having some centripetal acceleration, omega square. Let's say this is r length, so omega square r centripetal acceleration is here in this direction. So if I sit on this point, then I will feel that this is having some pseudo force in this direction. So at this, from this point frame which is accelerating in this manner, so here I am only taking the accelerating frame of this body, so it is accelerating in this direction. So pseudo acceleration would be taken as omega square r in this direction on each point on the body, that would be in this direction. But there is one more type of frame, that is rotational frame. So if I take a rotating frame about this point, so each point will be having some rotation, and with respect to this point, each point will have some minus omega square r vector in the outward direction. That would be the pseudo acceleration of each point, and that is actually equal to the acceleration of the object itself. And we can calculate the stuff from this accelerating frame. And if this object is also accelerating, this point is also accelerating, then we have to add, let's say this is a acceleration in the ground frame, then there would be some minus a pseudo acceleration also added along with this pseudo acceleration omega square r value on each point on the body. And okay, and the next points would be the mass distribution. So when there is any body, let's say this mass block of mass m, and if I put it on a floor, then each small element here, if I divide this whole length in some small elements, let's say dx, then each small element will apply some dn force. And because this is a uniform block of mass m of uniform density, above each element there is equal mass dm and so on. So what happens, how we decide that how much normal force will act? So it is decided by this fact that if I remove this floor, so what would be the tendency of the object to move towards this wall? So that tending acceleration towards this wall, when the normal force is removed, when this whole normal force is removed from this scenario, then what would be the tendency of the object to move downward? All of the masses, each of the dm mass has some tendency to accelerate with g acceleration. Since all of them have the same tendency to accelerate, then we can treat each of them as different, means like they are not even connected. In this case, means it is like this block is equivalent to having these two blocks which are not connected and placed on the floor. Means the normal force distribution is same in like dn force here, and same dn force distribution would be here, like here would be dn in this manner. So it doesn't matter how these two are connected, only for this case where all of the points have same tendency to accelerate. But let's say I take a cone, let's say I take a hollow cone in which there is only this boundary which is in contact with the surface. So if I remove the normal force, this point has some tendency to accelerate with g acceleration. If I remove it from other masses, means first try to split all the masses and see if all of them have the same tendency. So all of them have the same tendency to accelerate g acceleration. But if I put the floor there, these all g accelerations must be cancelled, but there is no surface in contact with them. So in that case, all of their masses gets distributed at the circumference of this hollow cone. So that's why this whole mass m can be treated as distributed around this ring of radius r of mass m. So we can assume that whole mass is distributed over this ring, and there will be some dn forces along this ring. But if I take a solid cone in which there are some internal points from which this body can contact, so what happens is that let's divide it into vertical sections first. So each mass of this body has tendency to go down with some g acceleration, but when I place the floor, this cannot have acceleration. And so what happens is that the mass first tries to apply force downward, and if it can be cancelled out from the bottom point, then it will not act sideways. So let's say this mass is dm1 and here this mass is dm2. So we can see clearly that this dm mass here is larger, and this whole mass will act on this area of cross section of this mass only and provide some dn2 force, while this mass will apply force on the cross section below it. Means they will apply the force on the cross section below it and they will get dn1 normal force. Here in this case, it was not possible that only this mass gets force according to its own mass, because these masses also need some force to be cancelled out, and that force comes from this mass. So we can treat this whole system like a hollow cone here can be treated like this, or let's say there is a triangle shaped body to make it more easy to understand. And if I divide it in some parts like this part has some, let's say, dm mass, and this part also has some dm mass. Each part has some dm mass, let's say. Then this mass only needs some dn1 force, and this also needs some dn1 force in the upward direction to be addressed. But because of the other masses above it has to provide the force that all of them need, and this point is to provide all of the force that all of the mass above it need. So that's why this whole mass can be treated as concentrated air, because this mass has to support the upper mass also. But in this case, this element does not have to support this upper mass, because this part will first try to apply force just below it. And if the mass just below it, because why it will apply force in this direction and not in this direction? First, this will happen because the acceleration is toward the gravity is tending to force it downward and not sideways. So first it will try to apply. So first this element will try to go downward, and if this mass tries to go downward, at first this mass below will apply some force on it to hold it, to not let it come down, while this mass will not have any force due to this. But if I remove this base part from this and it becomes this type of shape, let's say a hollow cylinder here. Now in that case this mass will try to go down, but there is nothing to stop it, so all of the force will go down from these points. And now it will become a little complicated how this force is distributed among the base. So we will not get such type of questions. In general we will get this type of question where either there is only a ring for force or whole mass is there and each column of mass is applying force directly downward. So these are the type of distribution of mass, and to get normal. And also this normal distribution, let's say there is one mass m placed here above this block, then this section, let's say these two are equal lengths, and let's say this is m mass and m mass. So let's say this is single block. This part of the block would have, this region will have some, let's say n force normal, and this region will have some 2n force because it has to balance this upper mass also. So the total force is 3n, but if we particularly talk about how this force is distributed, then we will see that this 2n force is in this region, which is equally distributed in this region, and this n force is equally distributed in this region. And this tells us about the torque acting. And so there would be some torque by the normal if I calculate it about this point, or let's say if I calculate it about this point, so this side will apply some higher force upward, causing a torque by the normal force in this direction. But there is also gravity which is causing some torque in this manner, cancelling out this torque by the normal. So net torque is 0 about this point on this body. And there is one more concept, that is alpha. So we know that when we have any body that is, let's say it is accelerating with some a1 acceleration, and I have another point that is accelerating with some a2 acceleration in the ground frame. So in the ground frame these are accelerations. Now if I sit on this frame, the observed acceleration of this body would be a1 minus a2. So this acceleration would be subtracted from this original acceleration in the ground frame. So this acceleration, that is a translation motion that is getting affected due to this translating frame. But if I say that this body is having some alpha angular acceleration, it is rotating, so if I take this frame, that alpha won't be affected. So I can take any translating frame like this points frame which is accelerating in this manner in circular path. I can take its frame which is accelerating in this direction, and I will see that this body, if this body has some alpha, the body will still have some alpha from this frame. It won't get affected due to this translating frame. So that's important thing, that alpha is not affected by any translating frame. And also omega is also not affected by any translating frame. Means if a body is rotating and you take any frame moving in a direction, then at that instant, if you see this body, the body will have same omega and alpha. But let's see, there is another case. You are rotating about this body, and also you are taking a rotating frame. Means initially your x-axis was in this direction, and let's say y was in this direction, and z was, let's say, upward. So what you are doing is not just you are moving in a circle, but you are also saying that your axes are rotating in this space your axes are also rotating. So when this axis rotates, we call it kind of rotational frame, and in that case this body will have this. In this case the body can have a change of omega and alpha, so these can be changed in this rotating frame. But if I don't change this axis, if I keep it fixed, like if this point goes from this position to this position, the x-axis still points in this direction, then in that case the omega and alpha will not change. So in rotating frame only the omega and alpha can change. And that's it. One more equation we will use, which is that if there is any vector a, let's say a cap unit vector, which is, let's say, moving in a space, rotating in a space like this manner, any manner which is changing orientation in the space with some omega angular velocity at any instant. At any instant this is rotating with some omega angular velocity, can be rotating like this or can be rotating in this manner. Means it can be moving and also rotating. So for the differentiation of this vector with time, that would be equal to omega cross a cap. And one more thing, omega cross some a vector, when this a vector, sorry, omega cross a vector, if omega and a are perpendicular, then we can simplify it to omega square a vector. So this is actually how we have the formula omega square r minus vector as centripetal acceleration. That is the same case as this, where this body is rotating in this manner while this r is perpendicular to this omega. So in that case we can simplify this to this form. But if it is not perpendicular, we cannot say that it is equal to this. And what are the other points? Okay, so we have the thing that is calculation of angular of momentum. So first of all, angular momentum, to use the conservation of momentum means L conservation, that only works when you calculate the L about any point. If you are calculating L about an axis, then it is not the total amount of angular momentum, and that is not any proper type of angular momentum, because the angular momentum is basically defined by some r cross p, this type of form, integration of this, there is the angular momentum, where r is a vector defined from a point. So whenever you calculate the angular momentum, that angular momentum is always defined from given with respect to any point. So, and when you take any point, you have to take the frame of that point also. So if this point is moving or accelerating, so you have to sit in that frame and apply the laws of physics and calculate the angular momentum in that frame. And let's say there is one point P moving with some velocity v here, and there is some p dash point on the ground that is not moving, and there is any object of mass m that is moving here in this direction with some v2 velocity. Let's say this is v1 velocity. So if I calculate lp about this point, these 2 points are very close, let's say it's the same place. So if I calculate angular momentum of this mass with respect to this p dash point, then it would be by the v2 vector m v2 vector, and this, let's say this is r vector from for both point, so it would be r cross m v2 vector. But with respect to this point, the velocity will become with respect, this is L with respect to p dash, while with respect to p I will take this as r into m bracket. This velocity will become v2 minus v1 from this frame, so I have to calculate from this frame v2 minus v1, and that would be the angular momentum from this point frame. Angular momentum conservation always taken when angular momentum is about any point. And while the linear momentum conservation, it is not calculated about any point, so you don't need to care about the frame. Okay, you need to care about the frame but not the point. So because linear momentum is not dependent on any choice of point, but it depends on frame. So if you are in an accelerating frame and these two are moving bodies, let's say there is one body here of mass m and it is moving with some velocity in this direction. So if you are seeing from the ground frame, which is inertial frame, this body will have some mv momentum. But if you are in an accelerating frame with acceleration, then this will have some pseudo force am in this direction. So because of this pseudo force, this body will have some external force. Even though it is a pseudo force, it is a force, and you cannot apply the conservation law because there is some external force acting, and so you have to be careful if you are in an accelerating frame. And talking about the calculation of L, that also follows same thing, but you have to add one more point, that it depends on point. But there is one more thing that is called L axis. L axis is generally used when we have to particularly deal with one component of the L. Means L, since it is a vector, it can be broken down into some components. Let's say there is an axis about which an object is rotating and it has some angular momentum in this direction and some in this direction, and if I need only this part, then let's say this part along the axis, that is called L axis. The only L component along the axis, that is the L axis, and the rest part is removed. So because L axis does not tell the total amount of angular momentum, we don't use it generally. This L axis is generally useful for calculation related with tau axis, torque about the axis, where torque about the axis is also not complete thing. Torque is generally calculated about a point, but this torque about axis is also useful for some restricted motion. Restricted motion means, let's say this is an axis and this body is able to rotate about it. So if I apply any type of force, it will not go anywhere, it can only rotate. So the only torque is about the axis, so that's why this quantity is useful. That's why we have this term. And so is the L axis. Both are related to each other, means this tau axis changes the L axis while this tau O changes the LO, and both are in the same frame. You cannot take different frames. For example, I cannot take the frame of P dash for torque and LP for angular momentum. Both have to be the same frame. So there is nothing big here. It is just that we have to be careful about how we are calculating, applying the laws properly or not.